Hi Rotoforge, Sam here. This is going to be a long one, but I think you'll like it. It's been a while since we posted anything, but after a few moves across the country, a few new jobs, and finishing a PhD, we're back on the project, and we finally managed to print some metal. We're here! We're alive! We didn't die in a basement in Chicago, and we're printing metal! Great! So, since you've seen what we can do, now we're going to take you back a little bit through some of the story, show you what we've done over the past 6 months to a year or so. And we just generally are going to walk you through where we've been and show you some of the pitfalls we've had along the way. And then we'll lead back into some of the more modern stuff like you've shown, and we'll show you some of the data we've collected. And then we have some hints for what's coming up in the future. Alright, stay tuned. So Rotoforge uses a process similar to additive friction roll bonding. And to show what that looks like, I have a substrate made of Play-Doh and a piece of Play-Doh that I want to try to bond to it using that process. So I have here a shearing tool, which is a piece of brass chucked in a drill. And what we're going to do is, rather than trying to use, say, a lot of downforce to try and deform one into the other, well, we can only do that locally, but we need relatively large amounts of force, or trying to rely upon some heating process where we heat and locally melt what we're trying to bond to the substrate, or the substrate itself, what we're instead going to do is very gently place our shear tool, in the case of Rotoforge, our wheel, and get it very close to our substrate, and then we're going to feed into that some of our feedstock. And then when we apply shear, we locally deform the feedstock, and using very low force, we can shear it into the substrate, and we can locally mix the feedstock and the substrate such that we can get strong bonding between them. In the case of aluminum, we can shear their lattices together to essentially produce a bulk aluminum part.
So, being the Cro-Magnon that we sometimes are, we decided to try and use the aluminum bell, the BLDC motors we had laying around and already on the printer, to do the friction roll bonding we wanted to do. And that kind of worked in little pieces. Maybe, it's hard to tell, not a lot of hope at the time, but just enough success to lead us on. Unfortunately, it also caused the magnets on the motor to get too hot and to lose a lot of their strength, so the motor's torque would decrease, and this would cause the motor to slow down and ultimately stall, especially since the bell is so wide, and that causes a ton of extra material to be spread out along the entire surface of the wheel, and that to increase the torque requirement of keeping the metal flowing. Plus, since it's made of aluminum, it wears down quickly and its surface is always changing shape. So we did the next logical thing. We went to McMaster and we bought some M5 thumb nuts, or thumb screws, that were made of A2 tool steel with black oxide finish, and had a knurled edge, and were just a little bit bigger diameter than the turned down bell of the BLDC motors. And that worked great. We got reasonably long deposits of up to 10, 15, 20 layers, and they had thickness and could be removed from the build plate and handled. That gave us some hope. So we decided to try and turn down the edges of the black oxide thumb nut to make it thinner and improve the resolution and improve the quality of the deposits. When we did that, we ran into a whole host of new problems, mostly having to do with the plastic wire guide and other elements of our system, the long, thin needle that we were trying to feed wire under the wheel with, as well as the tendency of the wheel to camber on the shaft of the motor. So, back to the drawing board. We started designing and ordering components from PCBWay to try and solve the problem. We gained more diameter to reduce process forces by increasing the wheel speed. We reduced the edge of the wheel down to 1.5 millimeters, which was the thinnest that PCBWay would make it for us, and we had them chrome plated to reduce the amount of aluminum that would stick to them. The larger diameter helps by making the wheel spin faster. Higher surface speed means lower cutting force, or lower deposition force. Plus, we had it lightweighted and turned to 1 thou tolerance to make it dynamically balanced. And we used the D-shaft hole on these wheels to make them compatible with various rock crawler motors or other standardized 3mm D-shafts. But then we made another mistake in doing so, in that the 3mm D-shaft is great, except it is very flexible, which introduced, once again, more wheel camber, especially with this new larger diameter wheel. It just flexes like crazy. And this causes the deposits to be wide and spread out. And because the wheel has sloped edges, this causes a ton of extra flash or just material to be extruded from the edges and make more or less unbonded sections around the deposit. So that was super annoying, and these wheels were not cheap from PCBWay. They were probably $30 or $50 a piece, I don't remember, but they were very expensive for what they are. And I understand why, because thinking I could save a few dollars, I decided to try turning my own out of H13 hot work tool steel from McMaster. Cut it from rod stock and turned it down on a lathe. And man, this stuff work hardens like crazy. It's reasonably easy to work with. It makes beautiful blue and purple chips. But it's hard to dynamically balance, and if you make it thin, it's prone to deflection and prone to forming burrs. It's hard to work with, to say the least. And making our own that were thin enough, meaningfully thinner anyways than the ones that PCBWay would make, well, it was possible, but it turned out to be really difficult. And we made the mistake of thinking, aha! We'll use the same rod stock and turn down 90% of it to make a 6mm shaft that's short and will be stiff so we won't have any camber or wobble. Fools that we were. Turns out that it's just hard to turn this much material away. It takes forever, and it tends to break tools, and man, you're fighting work hardening the whole time, and inevitably you end up bending or deflecting the thin edge you're trying to make, and once you've bent it, well, you can't really bend it back and keep it balanced. And if you don't want to make it to its final thickness on the lathe, well, you're going to have to machine it in post, and that tends to remove even more material and cause it to be unbalanced. We even went as far as turning it all the way down, trying to remove all the excess material, but these end up being too thin and too flexible because they aren't annealed yet, which H13 requires in order to reach its full strength and stiffness. So we went back to the drawing board again, and looking around at McMaster, we eventually encountered the concept of the slitting saw, which is a high-speed steel wheel which comes with a standard arbor of the right thickness that's nicely flared to provide support, and these saw blades are dynamically balanced to be able to spin as fast as 30,000 RPM. Plus, being made of already heat-treated and hardened high-speed steel, they have excellent wear resistance. They come in thicknesses from 3mm all the way down to 0.15mm, and they just do an excellent job of everything we were trying to do. We realized that we were trying to make our own saw blades from scratch, and we could just buy them for $6 or $8 next day shipping from McMaster. So, yeah. Buy commercial off the shelf when you can. So it was at this point, after about 2 months of messing around with O-Drive and are like various closed-loop brushless DC motor controllers and a bunch of software and firmware and electronics, and RC rock crawler motors with integrated brushless drives and various firmware elements whose safety features aren't fully documented, and custom chrome-plated H13 steel wheels on tiny 3mm D shafts. We kind of got fed up and decided to go back to the drawing board. There's just too many ways that these devices can fail, and trying to close the loop on their torque output is just not sufficient to keep their speed up when you're trying to print metal. It's too difficult to test and prototype. So out the window they went, and we decided to try turning down much faster spinning vacuum cleaner motors in order to get a free, we thought, 100,000 RPM high torque drive for our spinning wheels to try and further reduce the process forces, the torque requirements, and go all the way to 80 or 100,000 RPM. But they're a pain in the butt to take apart and virtually impossible to keep in one piece when you turn them down, so out they went too. Of course, at this point we were really at our wits' end and looked around the shop and saw that basically the only thing left was the Dremel 4300, a 180 watt brushless or brushed DCU motor with a flex shaft. So we grabbed a hold of it, hung it up on a peg over the top of the printer, and ran the flex shaft down to some clamshell mounts that would hold the flex shaft in place while we turned the Dremel on, and that just worked first time. To our surprise, the U-motor has a really optimal torque versus speed curve. It produces a ton of startup torque, and under load it has multiple passive torque compensating features for when its speed starts to reduce. Not only that, it has fewer electronics to fail under high current loads. It seems to be much less sensitive to drive voltage. It doesn't require any software or closed loop feedback to maintain a constant speed, and provides a ton of torque even at full RPM. Plus, they seem to be available at much lower cost, like much less than half the price we were paying for the brushless DC motors, and they spin faster to boot. So, I suppose there's a reason why people still use brushed DC motors and spindles for mills and drill presses and lathes and many other low-cost machine tools. Now we know. Naturally, following down this line of logic, we realized that the only thing stopping us from getting more reliable deposition was just adding more watts. And U-motors are probably the cheapest motor by far per watt you can buy, as long as you're not worried about weight or power density, that is per volume. So for the same price as the 4300, we just bought some Chinese flex shaft grinders from Vevor, 1,000+ watt units, more than a horsepower, and did the same thing we did with the Dremel. And they work great, as it turns out. They just work. It's like magic. Or really, I guess that's the magic of power. P is equal to F times V, force times velocity. The power dissipated by the wheel is how much force of friction is applied to the surface times how fast the wheel is spinning. If you can keep the wheel spinning fast enough, and you have enough torque to overcome the force of friction, you can make the metal flow any way you want.
Some of our first deposits were about 3 millimeters wide and 60 millimeters long. When cut in half and ground flat, they looked like they had complete density, and we started to get really excited at this point. So, with Core and Rob Herrick's suggestion and Random Lever Physics in the Universe suggestion, we decided to try and split the layers apart with a hammer, a framing hammer, and a X-Acto knife. And to our amazement, the layers don't come apart when struck with a razor blade, which was super exciting at the time. So we started to wonder, well, how ductile are these things really? Are they well consolidated enough to be folded over in a vise without delaminating? So we clamped them in the vise and hit them with a hammer. And yeah, sure as heck, they bend and fold just like you might expect a piece of plate or sheet metal to fold, at least of comparable temper. The failure mode that they experience at the bend is a little unusual because they've been highly cold worked, but it's normal for a highly cold worked aluminum grade like aluminum 1100 or 5000 series to exhibit this kind of cold cracking if you haven't annealed it before you go to hot work it. It's recommended that you anneal it between working cycles to retain maximal ductility and to prevent cold cracking whenever it's folded over a sharp bend or taken around a corner or something like that. But it's good to see, and we were particularly excited by the fact that the parts, as printed, still had more than enough ductility to go through a 90-degree bend and did not fail completely in brittle fracture when bent as such, and showed no signs of delamination at the bends. So here's another one, this time folding across the layers instead of through the Z-axis. And as you can see, it bends just like you might expect a regular piece of solid aluminum to bend. If you think about this in terms of comparison to like wire arc additive manufacturing, this is arguably far better ductility than you might see out of a typical welded aluminum joint. Of course, now that we collected this basic bit of quote-unquote mechanical testing, we became curious about deposition forces and eventually deposition temperatures. So Sam courteously set up a scale, a load cell on which we could print with a piece of aluminum stuck on top of a PLA printed block, and we started collecting deposition force data. Startup forces, when you go dive far too deep into the aluminum plate before you start actually feeding wire, are in the tens of newtons, but quickly fall to single digits, 3 to 5 newtons of downforce as the process becomes more stable and you reach something that looks a bit more like steady-state deposition temperatures. Of course, our process forces tend to decline towards the end of this run because the build plate is tilted and the engagement depth changes throughout the run, so there's a sharp rise in the slope from the start to the end of each deposition pass, and the wheel is getting steadily farther and farther away from the surface as we're printing. So it just, at some point, it fails to start and the deposition stops. But as you can see, the steady-state deposition forces are quite mild, even under less than ideal circumstances with relatively poor control. Of course, then we started to wonder, well, can we make this system any better? And we added a better extruder, 5000 series wire, more contact area for the wire going through the extruder, a thermal camera, a wheel cooling duct using a CPAP fan, preheating to the wire guide shoe, and a variety of other sort of control, quality of life features, and elements that we hope to be able to use to further reduce the deposition forces and give us access to stronger materials. And here's an example of a thermal camera run of printing 5000 series or 1100 series aluminum from our new thermal camera mount, courtesy of Sam. So once we'd collected this thermal data, we started to wonder, well, how strong are our parts really? So we sent a few out to a friend we have in the Bay Area to do mechanical testing in tension in X, Y, and Z, as well as in 4-point bend for some of our aluminum 1100 specimens. And to our pleasant surprise, they were as strong or stronger than H18 grade aluminum 1100, though the amount of elongation they exhibit in the Z is greatly reduced compared to the X and Y, probably because of the lower degree of grain elongation due to the direction of the force of friction the wheel applies, kind of like in a rolled sheet. But regardless, their overall mechanical performance is excellent and highly encouraging for future work. Then we started to wonder, well, do we have to only print in straight lines? Can we print at 90 degrees to horizontal? Could we print at angles by drifting the wheel? Can we draw circles? What kind of feed and speed control is required? So naturally, the most obvious thing to do is to try and do raster printing line by line, each line stacked roughly with a 50% overlap or 30% overlap or 70% overlap with the previous line until we could build up a line in the y-axis by printing multiple rasters along the x, hopefully using the minimum induction length or the shortest possible starting line length that we could feed and bond reliably with the wheel. It turns out that that minimum bond length is somewhere around 4 to 7 millimeters, perhaps less if you're craftier and have better control over volume feed and the rate at which the wheel is spinning and the temperature of the wire when it goes down. And the overlap fraction changes how well the bonding between the lines happens and how well the lines ultimately end up bonding to the substrate and to each other. So this footage you're seeing now is our attempts at printing horizontal lines in the y-axis that are exactly 90 degrees to the wheel rotation direction. And it kind of works. It's certainly doable. And if you go at longer lengths of line, if you print longer lengths, or if you print those lengths stacked, rastered next to each other over longer lengths in the X, longer stretches in the X, the resulting parts are better consolidated and certainly have better aesthetic qualities. So there's no reason that a printer like the Ender with no fourth axis is inhibited from printing objects with more complex geometries using our Rotoforge roll bonding technique. It just certainly gives up some aesthetic quality and it gives up some resolution in order to achieve that result, this is a big part of the reason we, later in the video, will talk about going towards a fourth axis and adding a bit more flexibility in printing curves. But before we do curves, we had to do diagonal lines. And we started with angles from 1 all the way up to 22 degrees in order to test how well we could drift continuously. As you can see from the insets, angles from 1 to 22 turn out to be pretty good, but the background footage of us printing at 27 degrees shows that there are some serious limitations to the volumetric feed approach in keeping the wire under the wheel and keeping the deposits well defined.
Michael, what are we doing in the near future?
We are developing a new printhead design, which is going to include a fourth axis, is going to be lighter in weight, it's going to have a shoe which can go to higher temperatures more controllably, up to probably 600 degrees Celsius, and it's going to have a more reliable wire feeder which can handle a wider range of wire diameters and wire materials without buckling or damaging their surfaces or other technical issues. Most of that work is currently being done on the new printhead for the fourth axis and the high temperature shoe to allow us to print steels, bronzes, copper alloys, nickel alloys, things like that with reasonable speeds. The current work on that is being done by Avery Lockwood, a member of our community, the high temperature shoe in the fourth axis that is. If you'd like to get more information about that, in the most recent information about that, you can go and check out her video at Avery Lockwood on YouTube. I'll put a link in the description below. She's been a big help and she's doing a great job on the design work and the simulation work on that side of things. Beyond that, beyond the strictly mechanical and thermal design constraints that Avery is currently helping us with, Sam and I are planning to broach an even wider material library, redouble our efforts on closing the loop on the wheel, the spindle motor, the temperature control of the wheel using both controlled part cooling and wire heating in order to get a much more well-defined thermal gradient at the contact patch of the wheel so that we can have better control of microstructure and start to do real materials science on, okay, how do our process parameters lead to final product properties? And how can we start to tune those properties to make parts with really desirable characteristics? And how can we start to tune those print parameters to allow us to print a much wider range of materials and maybe even start to do some material synthesis, which I'll produce a video about in the near future, explaining a lot more details about the kinds of science we want to do with this new platform and how we really want to expand the range of what's possible to make for everyone. So remember to like and subscribe and join the Discord if you'd like to join the discussion. We are always happy to have new faces around, new expertise, new ideas, and we're always open to discussion. If you want to build your own, you can pick it up on the GitHub and we'll try to help as much as we can. Thanks for watching, and go print some metal.